here are the starter questions for today. The first one's short and sweet. The second one, you may need to dredge up from your memory how you find displacement or distance on a velocity time graph. I'm going to reveal the answers now. So today we're going to continue numerical integration using rectangles to find an upper or lower bound, and we're going to see how we can do this efficiently on a calculator. So this is our general strategy for answering any of the questions. Very importantly, sketch a graph of the function you're integrating. You can do this on your calculator, but then please draw it on paper as well, because you'll need to draw some rectangles. Once you've got those rectangles drawn, you should be able to write down an expression for the sum of the areas of the rectangles. And finally, you can use your calculator in a very efficient way to add up all of these rectangle areas. If you have a question that involves some trigonometry and we're doing some integration, you must be working in radians, so just make sure your calculator is also working in radians. Okay, so now we're going to try a proper example and apply a sensible structure to work out a lower bound for the integral of cos x squared going from 0 to 1.2. Okay, so the first thing that's sensible to do is to see what the graph looks like. So if we go to your calculator, let's see, right, and we want to go into your graph mode. So I've got it on graph mode already. I'm going to type in cos of x squared. Okay, execute. Let's see what it looks like. It's not looking pretty, so there's a few things to check. I could do view window and just do my initial axes to get something sensible. Still not very helpful. And then the other thing to check is, because we've got trig and we're doing integration, it's a really good idea to check if I'm in radians. So I've done shift setup and I'm going down, there we go, angle, and I can see I'm in degrees. I need to be in radians when I'm doing calculus with trigonometry. Right, so if we draw it this time, that looks a bit nicer, but we only need the bit from 0 to 1.2, so we're going to zoom in on that. So F2 is the button for zoom. I'm going to draw a little box around the bit I want, so I press box. Okay, now go a little bit down into the left of my origin. I'm going to press execute, and that'll be my bottom left corner of my box. I'm just using the arrows to go up to cover the bit that I want. Okay, that'll do. Execute. That looks nicer. Okay, now the lovely thing is we can get an estimate of the integral from your graph mode, and that will be helpful for checking our answer is sensible. So let's use gsolve, and then I can't see integrate here, so I press F6. There we go, there's a little integral dx sign. So I want to integrate my graph from x is 0, so I just press 0. There we go, lower bound. Press execute, and my upper bound is 1.2. Press execute. Lovely. Coloured it in for me, and there we go. I have a nice estimate that I'm going to jot down. Okay, and compare that with my answer at the end. Right, lovely. So let's have a look. We know what the graph looks like now. We can think about trying to draw our rectangles. Okay, so here we go. Here's our graph. Done my little sketch. I need to now split it into 6 rectangles. I'm going from 0 to 1.2. I know they're going to be 0.2 wide. There we go. And I want to find the lower bound, so I know that my rectangles are underneath the curve there. Okay. Right, so my estimate, my lower bound, is going to be the sum of the areas of the rectangles. Okay, so I'm going to do base times height for every one of those 6 rectangles. It's easier if I just do base times the sum of the heights. Okay, so the base was, if we do the full width there, so we're going from 1.2 down to 0, divide that by 6 pieces, we get 0.2 for each one. So my base width is 0.2. To get my height, if we have a look here, we can see that it's always, for this particular graph, it's the right-hand side of the rectangle that touches the curve. So to get the height of my first bar, I go to the right-hand side there. So I want to work out the y value when x is 0.2. So I'm going to do cos of 0.2 squared. And for the next one, the next right-hand side is going to be cos of 0.4 squared. And along the next one is going to be cos of 0.6 squared, and so on. And my very last one will end up being cos of 1.2 squared. It's the right-hand side of that rectangle. My graph is immensely helpful for me to know what I'm doing. Okay, so here's my calculation. Right, now that looks really tedious to put into the calculator, so we're going to look at a really efficient way of doing that instead. So I'm just going to go back to the calculator and we'll have a little look. Right, so on here I'm going to go to my run mode. Alright, and we want to do 0.2 times the sum of a sequence of numbers. So how do we do that? It's like a list of numbers. So we do options, then we press list. Okay, and here are all the list things. So let's have a look. We want to have 0.2 times a sum. So if you press, I can't see sum at the minute, so I press F6. I still can't see sum. Press F6 again. There we go. There's a sum. The sum of what? The sum of cos 0.2 squared plus cos 0.4 squared and so on up to cos 1.2 squared. So that's a sequence of numbers. So if I press F6 again until I see sequence here, okay, what is my sequence? It's of cos of x squared, okay, where x is my variable and x goes from 0.2 up to 1.2 in steps of 0.2. Okay, right, so now there we go, we've got that number calculated straight away. So we'll go back in and write that down. Okay, so that's the steps on the calculator, so you can refer to it later, and we get 0.8790 and so on. Okay, now we need to remember that we're looking at a lower bound, so really we ought to round down for that so we don't accidentally step over too far. Okay, so we get 0.879. That's it. Let's do another example. This time we're going to use 4 rectangles to determine an upper bound for the integral of natural log x squared plus 1 from 2 to 6. So first of all we need to sketch a graph. We're going to draw the graph of natural log x squared plus 1. So you go into graph mode, okay, and type in your function. So natural log x squared plus 1 and enter, and then draw it and see what it looks like. So I can't see a very good view at the minute, so we'll press view window, so that's F3. Okay, and I'm just going to press initial. Okay, now I know that I need the graph from 2 up to 6, and I know that that goes up to 6, so that's absolutely great. So let's look at the area that we want. So we press G solve, which is F5, press F6 until we can see the integral, and when we simply type in our lower bound, so x goes from 2, so I'm just going to type 2 and execute, and then we want to go up to 6, and then we execute, and it finds that area for us, and we now have an estimate of the area. So now we can also sketch the graph. We can start thinking about drawing rectangles on it. So we have a range going from 2 to 6, and we need to fit 4 rectangles. So if we do 6 take away 2 and then divide it by the 4 rectangles, each rectangle will be of width 1. Now we can find the areas of the rectangles. So we're going to write down an expression for that. So it's base times height for every rectangle and add them up. You can take the common factor of base out and add up the heights. And we're looking here at where the curve meets the rectangle. So for every rectangle, the curve meets the rectangle at the right hand side. So we're going to substitute the right hand side coordinate of the rectangle into y equals natural log x squared plus 1. So x is going to be 3, 4, 5 and 6. Now in the question it says determine, and there was an exam question on one of the sample papers where they then required you to do some calculations of the numbers. Even though we're working with natural log and we can use a calculator, they still wanted us to kind of simplify the terms before calculating. So that's why I've written this line here. I've just worked out what 3 squared add 1 is and 4 squared add 1 and so on. We could get rid of the 1 times at the start of this. You can simply type that into your calculator as you see it, or if you'd prefer, you can use the sequence system as I showed you in the previous example. Whichever method you choose, you should get 12.0048 and so on. So there we go, we have an answer. It's pretty good, it's a little bit above the one we were expecting, 11 point something. Remember, we really ought to round that one up because it's an upper bound, so I'm going to put 12.1, but you wouldn't be penalised, I don't think, if you put 12.0. So now we've got some questions for you to try. They're all multiple choice. If you have a little go on some paper and using your calculator by pausing the video and then unpausing it and checking if you're right. There are worked solutions to this on the accompanying PowerPoint if you'd like to see it. Here's the first question, so pause the video and have a go. I'm going to reveal the answer now. Here's the second one. Pause the video and have a go. I'm going to reveal the answer now. Here's the third question. Pause the video, have a go. Now I'm going to reveal the answer. Here's the fourth one. Pause the video, have a go. And the answer should be C. Here's the fifth one, getting a little trickier now. And the answer is B. The last question is more challenging, but if you write your expression out clearly, it should be straightforward. So, pause the video, have a go. I'm going to show you the answer now. So you can have a go at some questions from exercise 15A and mixed practice 15 in your textbook. There are worked solutions as well as answers on the electronic version of the textbook, or you can look at the accompanying lesson notes for both the questions and the answers and work solutions. If you want to have a go, pause the video, have a go. I'm going to reveal the answers now. You can have a go at these questions and pause the video. And here are the answers.